all the devices around us need some form of energy to work. And if you notice, most of them use electrical energy. Today, we try to understand the mechanism of electric current. But before going deeper into the course, we should try to understand what we did before. Before, we understood the electrostatics. Means we have seen the situation where the charges were at rest. Now, we'll try to understand what will happen if the charges will start move. But wait, how can we move a charge? Yeah, we can move a charge but applying any external electric field. And how can we do that? Let's try to understand. So, we'll start by understanding the mechanism or inside story of any electrical conductor. Here I have a cross section of any copper wire for you. Try to understand. If you notice, here I have written the configuration of copper, in which you can understand that copper has 9 electrons in the 3d orbital and 2 electrons in the outermost 4s2 orbital. Thus, after getting a very little amount of energy, what will happen? It will try to stabilize itself, in which what is really happening, as you can see here, the electron from the 4s orbital jump to complete the 3d orbital. Thus, this copper will reach to its stable state. Now, at this point of time, this copper only has the one electron, that is 4s1 in the outermost orbital. Thus, they are free to rotate. While rotating, whenever they get a little amount of energy from nowhere, then also they are able to do the transition within the different atoms. As you can see here, like how the electrons are doing the random transition. At this point of time, the transition is actually completely random. But the speed at which they are moving or jumping from one atom to another comes out to be around, I'll write here, V electron comes out to be around 10 to the power 6 meter per second, which is quite large. But then also, as the transition is completely random, we'll say that the net flow is 0. Now, what will happen if I apply the external electric field? Let's see. Here you can see I have applied the two plates, one negative and one positively charged. What will happen if I try to observe what will happen to the charges or the electrons? As you can see, due to this electric field, the electrons will try to travel from the negative plate to the positive plate. What is happening? The negative plate is pushing a single electron to the nearest atom, and then due to repulsion, that atom is jumping into another atom and then again another. So in this way, all the electrons are get drifted in a particular direction with a particular velocity. This flow of electron is actually the electric current. Now, I think you know the intuition of the electric current and also why electric current is only possible in metallic conductor, as they have the free electrons. Now, let's try to understand the direction of the electric current. Actually, Benjamin Franklin around mid-17th century thought that positively charged bodies had certain amount of fluids in them, and at the same time negatively charged bodies had deficiency of that electrical fluid. When he tried to put the two bodies in contact, that is positively charged bodies and the negatively charged bodies together, he saw the electric current, and he thought that this electrical fluid is now flowing from positively charged bodies to the negatively charged bodies. Thus, he defined the electric current or the flow of electric current is from positive to negative. But soon after the discovery of electron by J.J. Thomson, we come to know that electrons are the real charge carriers. Thus, we define the electric current as the flow of electron that will be from the negative terminal to the positive terminal, or the negatively charged bodies to the positively charged bodies. But the convention given by the Benjamin is stuck. Thus, we always say that the direction of electrical current is from positive terminal to the negative terminal, or from high potential to low potential. Now, let's try to quantify the electric current mathematically. How can we do that? So as you can see here, we define the electric current is nothing but the flow of charge. We are not saying which charge. To quantify it mathematically, we simply say that electric current, let me write out here, we simply say that this electric current that we will be denoting with I is nothing but the number of charges flowing per unit time. Now, how can we denote this thing? So I, number of charges flowing is nothing, we say Q divided by T. This is the general formula to quantify the electric current. Now, at the same time, we also have two more values for electric current. The first one is nothing but known as instantaneous current. That is the current flowing in any particular instant. So, for that, let me write out here, we say instantaneous current. This we simply define as I instantaneous is nothing but dq upon dt. That is dq amount, very little amount of charge flowing for very little amount of time. This is known as instantaneous current. Apart from this, we also have the average current. Average current, how we define it? Average current. To quantify average current, we simply say I average is nothing but delta Q upon delta T. That is the change in the charge flow to the change in time. Now, let's talk about the unit of electric current. So, unit of electric current is ampere. It's again just after the name of the scientist who invented it. We denote it by capital A as its dimension. Now, let's try to see some examples on its basis. So, suppose there is an equation given to you. The equation is like Q equals to 2t square plus 3t minus 2. What this equation is doing? This equation is telling about the charge. This equation is telling about the charge. That the charge is a function of time. With time, the amount of charge will also vary. If we have to calculate, let's say, instantaneous current at t equals to 2 seconds and 4 seconds. Let's try to find its value. So first we'll calculate for at t equals to 2 seconds. How can we do that? We know that I instantaneous is nothing but dq upon dt. What we have to do? We just have to simply differentiate this equation with respect to time. What we'll get? We'll get 2t d upon dt in bracket plus 3t minus 2. Doing simple rearrangement, let's see what I'll get. I'll get I instantaneous is nothing but we have squared, we'll get 4t plus 3. Now, this is the value of our instantaneous current. At t equals to 2 seconds, we are calculating. Thus, I just have to put 2 in place of this t. What I'll get? I'll get 4 to the 8 plus 3. It's 11 ampere. This is my I instantaneous at 2 seconds. Now, we have to also calculate for 4 seconds. What we'll get for 4 seconds? Let's try to see. For 4 seconds, if we try to calculate, we'll simply get, again, just we have to put the 4 in this equation. This is the equation of the I instantaneous with respect to time. So, I instantaneous at 4, we'll simply get 16 plus 3, that is 19 ampere. Now, we have calculated the instantaneous current at 2 and 4 seconds. If I'll ask you what will be the average current, that is average current, what will be the average current from 2 to 4 seconds, then how we can calculate this? Again, there are two options. What we can do, we have the value of I instantaneous at this 4th second and this 2 second. We can simply add them and divide it by 2, means we are finding the average of the instantaneous 4th and 2. Or we can do by solving this I average that we have just calculated, that is delta Q upon delta T. Delta Q, what is delta Q? This is nothing but the change in charge, change in amount of charge or change in charge. This is amount of change in charge. So how can we calculate it? If you recall, this is our equation, 2t square plus 3t minus 2. Now, I'll write it just here. We have Q equals to 2t square plus 3t and this minus 2. This minus 2. Now, let's try to calculate Q at 2 seconds. So, what we'll get? We'll get 2 into 2 square at 2 seconds. This is what I am calculating. We'll get 2 into 2 square plus 3 into 2 minus 2. What we'll get? 8 plus 6 minus 2 means we'll get around 12 coulomb of charge at 2 seconds. Now, let's try to calculate the amount of charge. Try to calculate the amount of charge at 4th second. So again, following this equation, at 4th second, at 4th second, what we'll get? Putting the values Q at 4, we'll simply get 2 into 16 plus 3 into 4 minus 2. Solving this, we'll get 32 plus 12 minus 2. We'll get 42 coulomb. Q4. Now, again, putting it in the current average, I average expression, that is nothing but change in the charge delta Q means Q4 minus Q2 upon time, that is 4 minus 2, because we have to calculate the average time between 2 and 4th second. So what we'll get? We'll get I average is equals to Q4, that is 42, minus Q2 comes out to be 12 upon 2. It's nothing but 30 by 2, that is 15 amperes. I hope you got the concept that we have discussed so far. Well, as I was telling you earlier, one can also calculate the same I average by calculating the average of this 11 and 19 ampere. If you try to calculate 19 plus 11, 30 divided by 2, you will get the same value as 15 amperes. Well, that's all for today. We'll meet again and discuss how we should categorize this electric current. Why so? Because we know how to quantify it, we know the direction. Now just try to think whether it's a scalar quantity or vector quantity. Well, we'll try to understand this in the next video. Till then, stay connected with Tutorac.